Before we move on to discussing the rotation tensor, it is important to discuss two operations on tensors which we have so far ignored. Those are the inverse of a tensor and the determinant of a tensor. As you may guess, these definitions will carry forward more or less as they were in the case of matrices. So here is a definition for the inverse of a tensor. The inverse of a tensor A, denoted by A inverse, is the tensor which satisfies this operation, that it operates from the right or from the left, and the answer is always the identity tensor. Now let's think about this identity tensor. The identity tensor is the tensor which operates on any vector A to produce the vector A. Now you can show that in any coordinate system the matrix of the identity tensor is always the same. It is always 1 1 1 0 0 0 0. Okay, so what this tells me is that the inverse of the tensor A is independent of the coordinate system that you are working in, and it also tells us that in order therefore to find the inverse of a tensor, pick any coordinate system P, find the matrix of the tensor A in P, compute the inverse of the matrix, and that inverse of the matrix will be the matrix of the inverse of A. Okay, so let's kind of go over that again. So what we are saying is that I want to compute A inverse, by which I mean that I want to compute the matrix of A inverse in some coordinate system P. So what I want to do is matrix of A inverse in P, and the way you calculate that is first you take A, compute the matrix of A in the same coordinate system P, and then find the inverse of the matrix. So this is inverse of the matrix of A in P. Okay, so that's what this line is saying. Once I have the matrix of A inverse in P, I can use formula that we are going to do later to find the tensor in any coordinate system I wish to find it. Okay, so that is the inverse. Another thing that you may already know, which carries over from matrix algebra, is that A inverse will only exist if A has no zero principal value. There are going to be no tensors in this course which are not invertible. I have just given you this information just to connect it with knowledge you already have. Okay, let's come to the determinant. The determinant of a tensor A is found by this formula. The determinant of the tensor A is simply the determinant of the matrix of A in any coordinate system. That means that the determinant of A is independent of the coordinate system. If I give you a tensor A, pick your favorite coordinate system, compute a determinant of the matrix of A in that coordinate system, and that is the determinant of A in any coordinate system. Okay, so here are some properties which you would be familiar with something like this from matrix algebra. So the inverse of the composition of two tensors is the composition of their inverses with the order reversed. The inverse of the transpose is the transpose of the inverse, and therefore it has, you don't have to worry about the brackets, you can write something like that. The determinant of A inverse is simply 1 upon determinant of A. Okay, so therefore we already saw that A inverse exists only if A has no zero principal value. Okay, if A had a zero principal value, determinant of A would be 0, and this would not be defined, but that is because this is not defined. Okay, alright, so that is all about inverses and determinants. Moving on to rotation tensor.